Hello, thank you all for coming out today. I know it's very cold, so I appreciate it. Yeah, today I'm going to be talking about the denudation of the Weald. And yeah, it's not something that I've spent a lot of time working on. And so the research around the denudation of the Weald is not really finished. It's more of like an ambition. And hopefully I can show you the sorts of things I'd like to do in the Weald over the next few years. And the reason why I'm talking about it today is because Richard asked me to talk about the denudation of the Weald. So yeah, bear with me. I hope I can tell you a nice story about the Weald, but I expect there'll be a lot of people here that know a lot more about the Weald than I do. I am from London, but I spent a lot of time in different countries before coming back to UCL. And I moved to London, and I've only recently moved to Balcombe, which is right in the centre of the Weald. So this is still sort of not very familiar geology to me. So if you have any ideas about what I should do, please tell me. Denudation, I know that some of you haven't heard this word before. It basically means erosion. So it's the erosion of the Weald. Okay. Now, yeah, normally I study mountain belts. And so normally when I give these sorts of talks, I say, why do I study mountain belts? And it's because I get to go to places like this. This is the Borehole in the Central Alps, so the Swiss Alps. And this is where I did my PhD work now. And yeah, you can see that it's spectacular. And really the reason why I got into geology and study mountain belts is to go to these sorts of places and visit these sorts of places in the world. But realistically, there's a whole reason to study mountain belts besides just going on nice field trips. They modulate climate through weathering reactions. So this is the idea that minerals in rocks, as they're exposed, react to carbon dioxide in the atmosphere, and that ultimately draws carbon dioxide out of the atmosphere. Sediment is sourced from mountain belts, so if we're going to understand sedimentary basins, we need to understand where the sediment is coming from. Exhumation of mountain belts, so this is the motion of rock towards the surface, as opposed to denudation, which is more the lowering of surfaces. Exhumation is the opposite, effectively, but it's the same sort of thing. It's the erosion. Exhumation brings rocks from depth to the surface, and it's really through this process that we're able to understand what the rocks look like at depth. Right? If they didn't come to the surface in mountain belts, we wouldn't know what they look like. In terms of natural resources, today, lots of things like copper, lithium, the things that we need are found in mountain belts. And then there's also seismic hazards associated with mountains and growing mountains. And very recently, people have started to focus more on mountain belts and speciation and thinking about how mountain belts control biodiversity. And that's sort of a really sort of blossoming field at the moment that's really only sort of started to, I guess in the last sort of 3 years, people have really started to think about it. Probably as a result of COVID, I guess. So this is a very famous cross-section through the Alps, and it shows these naps. These are basically slithers of the oceanic, or sediments on the oceanic crust as it was subducting underneath the Alps that have been scraped off and stacked on top of each other to produce these famous naps. And this is a sandbox model simulating that same sort of process. And I'm showing this really just to highlight this relationship between erosion and mountain belts. So here, this is sand that's just colored to show you how it's deforming. And there's a piece of material at the bottom that's dragging the sand from the left to the right. And as the sand is being dragged, it sort of slams into this backstop, and these thrust faults develop. And the thrust faults develop, and initially when the model starts, these thrust faults develop and migrate towards the left. But then over time, the sand grows above this black line, and effectively this represents surface erosion. And in this case, somebody comes along with a vacuum cleaner. It's probably a student that's vacuum cleaning this. As the sand grows above this black line, it's being removed. And that process is simulating erosion. And hopefully what you can see is that as the material starts to be eroded, we have the end of this sort of propagation of thrusting towards the left, and we have sort of rapid exhumation and the exposure of these deep rocks in the core of this sandbox model. Okay, have you seen this sort of thing before? Is this? I'm not sure what people know. So if something's unfamiliar, please interrupt. Of course, this actually takes a very long length of time. The sand is moved very, very slowly, and a student would have to be here for the best part of 2 days removing the sand. This is a slow process. Okay. Fortunately, we can also do the same sort of thing using numerical models. So this is a T-box, well, it's a bit complicated, but essentially this top panel is a numerical model simulating the processes that drive erosion. So simulating the development of rivers and sediment transport by rivers out of the mountain belt. And this bottom panel is showing how the crust is deforming as the rocks collide. And the reason why I'm showing this is to get across this idea that the climate and changes in climate can change the precipitation, and that change in precipitation can change how the mountain belt deforms. So during this middle period of time, between 20 million years and 40 million years, there's enhanced precipitation, and that leads to higher rates of runoff and more erosion, and the mountain range actually becomes narrower. Okay, and this is because the faults that are controlling the size of the mountain range have to respond to that change of mass. So ultimately, the faults are slipping only when the conditions are right for them to slip. So only when there's the correct stress conditions. Okay, so we would like to understand mountain belts and erosional processes to understand how erosion rates and tectonics are linked in mountain belts. This idea that erosion can actually influence the tectonics is probably something that really came about in the mid-90s, and lots of people have been trying to solve this for a long time. And this is something that I'm still working on. If we'd like to understand erosion, we'd also like to understand the physical processes that are driving erosion. In this photo, you can see places where the rocks are fracturing. The rocks are fracturing, and then these have been transported by glaciers. You can also see places, maybe not so clearly, maybe here, where the rocks are being polished by the material that's being transported by the glacier, basically sort of wearing away the rock and making these smooth surfaces. And then around the side, we can see these glacial moraines. So by studying erosion rates in mountain belts, we can understand how erosion actually operates. And then we can also think about this in fluvial systems. This is a really nice example from the Apennines, the Reno River, just upstream of Bologna. It's beautiful. And we used to take the students here when I was in Switzerland to look at these sorts of landscapes. So this is a river, obviously, and at the bottom of the river there's this fluvial gravel, which is being transported by the river. And then if we look higher up in the landscape, we see almost exactly the same sediments that are perched at this higher position in the landscape. And so this is showing us the time when the river was actually at this height. And so between the deposition of these fluvial gravels and the modern day, there's been this much erosion and this much incision. So this is about 20 meters of incision. And so if we can date the sediments at this elevation, we can calculate how quickly this river is cutting down. So essentially how quickly the landscape is denuding, or what the denudation rate is. In terms of what we can actually measure to understand how mountain ranges change and ultimately how the Weald evolves over time, we can measure exhumation. So this is the motion of rock with respect to Earth's surface. And I'm showing this cartoon here where you can see these dark sand layers that are moving towards the surface of the model. And we can actually measure that. I guess people are familiar with metamorphic rocks and the idea that these rocks have been buried to great depth and then they've come to the surface. And that's a clear indication that there's been exhumation. We can also measure rock uplift. So this is an example here. This is a marine terrace from California. And you can see this marine terrace is incredibly flat. And it formed when the sea level, when this rock surface was actually at sea level. And so between the formation of this flat surface and today, the rock has moved up with respect to sea level. And so these are slightly different definitions. But it's important when we think about how landscapes evolve, because in this case, we're bringing rocks upwards, and we're doing work against gravity to lift these rocks up. Whereas in this case, we're really just moving rocks up, and they're filling the void that's left due to erosion. And so if we're going to understand surface uplift and how surface elevations change through time, we need to understand both this component of rock uplift, so how quickly rocks are moving up, and also exhumation, or how quickly the surface is moving down. And this is really important when we try and think about how landscapes evolve and what the Weald might have looked like in the distant past. One of the key tools that I use in my research that's not about the Weald is related to river profiles. And so I'll talk a little bit about this at the end, but basically we can look at the shape of river profiles and use them to tell us something about the previous tectonic histories that an area has experienced. Okay, so normally I work in sort of mountain ranges. These are two examples that made the news relatively recently. I was looking at Mount Everest and trying to understand how Mount Everest is growing today and how much of that growth is related to recent erosion as opposed to long-term tectonic processes. And then I was also looking at Yosemite Valley to try and understand how quickly the valley that we see in Yosemite Valley developed. So normally I would talk about these sorts of things, but today I'm talking about the Weald. Yeah, I'm also working on this. This is what I'm currently looking at, these very deep fjords that are basically eating away along the Antarctic Peninsula. So there hasn't been that much work on the Weald in terms of understanding the denudation of the Weald. And I think this is the most recent paper that really tried to explain the denudation history of the Weald. And this is by David Jones in 1999. And he looked at, or he synthesized the data along this profile here, where this is the Weald. These are the chalk hills that surround the Weald. Where are we now? We're sort of here, is that right? Or are we here? Here? Yeah. Okay. I'm down here in Balcombe, so that's where I am. So I'm right in the core of the Weald. You're hardly in the Weald at all. And so he produced these cross-sections like this that showed what the Weald might have looked like before. So basically he attempted to project the strikes and dips or the way that the beds or the angles of the beds up over the core of the Weald to try to reconstruct the height of the Weald and produce these oops. Yeah, okay. So he produced this figure that essentially showed how much erosion there has to have been between when the Weald was high like this to how it is today. And this led to this figure that shows the long-term rates of denudation and the total magnitudes of denudation across the Weald. And so in the central part of the Weald, here, where this is the South Downs and this is the low Weald and this is the high Weald, and then we're sort of here. Right, is this? Right between the green sands and the North Dales. And these long-term patterns of denudation show this bulge in the middle. And average rates of erosion are about 0.02 millimeters per year over the last 66 million years. So that's quite a slow rate. Typical rates in mountain belts might be about 1 millimeter per year to maybe 10 millimeters per year in somewhere like Taiwan. In the Alps, they're probably around 1 millimeter or 2 millimeters per year. So these rates are incredibly slow. But this is just an average, and probably there are times when there are faster rates of erosion and times when there are slower rates. And by looking at how the different sedimentary deposits interacted with one another, David Jones decided that this scenario was the best, in which there was a large amount of Paleogene denudation or erosion, a smaller amount of Neogene denudation, and then a very small amount of Quaternary denudation. And this is quite different to some of these earlier models that people have suggested in the past. But really, since the publication of this figure, there's been very little work to try to understand how the denudation pattern has changed across the Weald as a function of space and time. So have there been pulses of higher erosion rates, or have there been spatial variations in which one area eroded first and then a different area eroded later? And so I've got these two different sort of n-member models that I think is an easy way to think about the two extreme scenarios. And the first is this idea that the Weald grew, and there was this very, very high mountain range. It probably wasn't a mountain range. It was still maybe 2 kilometers high at the core. And I've got this figure here of Sisyphus pushing this boulder up the hill, and this nice quote by Albert Camus. So the struggle itself is enough to fill a man's heart. I think that rings true for geology, for sure. And so I enjoy the struggle, even if I don't ever get to the answer. But in this scenario, the Weald grew, and then it was eroded. And for the Weald to grow and then be eroded would require an enormous amount of stress, essentially. So there would have had to be a lot of compression from the north and the south to basically lift up the rocks that would have made up the core of the Weald to these high elevations of about 2 kilometers, maybe 1.5 kilometers. And so this would require a lot of work to essentially lift up these rocks. And then the other scenario, this other n-member scenario, is that as the fold was developing, erosion was essentially keeping up. And so anytime you had a small amount of uplift, you would have erosion immediately after that. And I've got this nice figure here. This is actually a mountain range in Colombia. This is the Sierra Nevada de Santa Marta mountain range. And the idea in this mountain range is that there's this very low relief surface at high elevations. And as the mountain is growing, glaciers are developing at these very high elevations. And glaciers are much more effective at eroding rock. And so these glaciers are building this flat surface in situ. And it's called the glacial buzzsaw hypothesis. This idea that as the rocks grow, the rocks are buzzsawed away. And I guess we'd call this a circular saw, but that doesn't have the same ring to it. And this is important because if this is what's happening in the Weald, then it would be much easier for the Weald to develop. And this has far-reaching implications for the sorts of geodynamic processes that produce these kind of features that we see. So this is an example of what the Weald might have looked like if we think that it developed based on that sort of n-member 1. This is the Shillong plateau, and this is just south of the Himalayas. And you can see that there's this low relief surface that's at high elevations, and it's sort of got a fold to it. There's certainly a large fault here, but in general you can see that there's a, well, can you see that? Like, sort of. But this is an example of what the Weald might have looked like. The elevations are about 2 kilometers with respect to this base level. And the widths are similar. But here we're 150 kilometers south of the Himalayan thrust fault. And the idea is that the thrust fault that built the Himalayas jumped towards the south, just like in that movie of the sandbox experiment that I was showing you. The fault jumped to the south, and that uplifted this area. And so to do that would require a huge amount of strength on these faults and in the rocks that are being pushed together to drive this plateau to these high elevations. Importantly, the Weald is 700 kilometers from the Alps. So in terms of comparing the Shillong Plateau and the Himalayas to the Weald and the Alps, the distances are just completely different. So one of the tools that I'm trying to use to understand this is called thermo-chronometry, which is essentially thermo, so the heat, and chronometry, which is time. And this was really developed by Strutt in 1905, so quite a long time ago now. But the idea is that when different crystals develop and different crystals grow, they incorporate uranium and thorium and samarium into their structures. And these radioactive elements decay and produce alpha particles, which combine with electrons to produce helium atoms. And at high temperatures, all of the helium that's produced in these crystals can escape, in the same way that helium can escape from a balloon after like a kid's party or something. But then at low temperatures, the helium is retained in the crystal. And because we can calculate how quickly the helium is being produced by measuring the amount of uranium and thorium in the mineral, we can convert the amount of helium into an age. And this principle is really what we use to date different minerals and different rocks. But the unique component, or the unique aspect of the uranium, thorium, helium system in apatite is that the helium can escape. And so when we calculate an age, we're not calculating the age that the mineral formed, we're calculating the age that the rocks cooled below about 100 degrees Celsius. Does that make sense? Is that okay? And this is because the helium is lost through diffusion, and the diffusion coefficient is temperature dependent. So yeah, at high temperatures, helium can escape very easily, and at low temperatures, it's locked into the crystal lattice. And so if we have a rock that experiences this time versus temperature history, so at 20 million years ago, the rock is at 150 degrees, and then it cools over time as it's brought from depth towards the surface. The amount of helium in the crystal changes like this. So at high temperatures, all of the helium is escaping, but then at lower temperatures, the helium starts to increase at a constant rate. And it's increasing at this rate because that's the rate at which the helium is being produced by radioactive decay. Okay, so we would call this then the closure temperature of the system. So the closure temperature of the uranium, thorium, helium system is about 75 degrees Celsius, maybe 100 degrees. It depends on the specific situation. But that corresponds to a few kilometers deep in the Earth. Okay, and there's a whole host of different geochemical tools that allow us to date how rocks cool over geological time. So I'm talking now about the uranium, thorium, helium system in apatite. but there are systems that record cooling from temperatures of about 800 degrees. And what this allows us to do then is reconstruct a rock's history as it travels from depth towards the surface. And as it travels from depth towards the surface, it's telling us about the denudation of the surface, so how quickly the material is being removed from above that rock. The other system that we use a lot is apatite fission track dating, and this is essentially the same system or the same idea. That here the uranium decay produces these fission tracks, so small defects in the crystal that are about 16 microns long, and at high temperatures the tracks can sort of be mended by energy in the crystal lattice, but then at low temperatures there's not enough energy and the tracks remain. And so you can count the fission tracks in a crystal of apatite, and that tells you how long that rock has been below a specific temperature. And this temperature is a little bit higher than the uranium, thorium, helium system. It's more like 110 degrees. So this pair of dating tools allow us to track how rocks come to the surface over the sorts of temperatures that are important for erosional processes. So yeah, initially when they form, they're these long, wide tracks, and then if they get hot, they get shorter until they disappear. I don't think I'll talk about this because this is just about how we actually count these tracks. But if you've got any questions about how this actually works, then that's okay. These are what fission tracks look like. So this is an apatite crystal here. And this distance is probably about 200 microns. And so these tracks are like little small defects in the crystal. And you can actually see them with a microscope. It's really amazing. And this is the mica. These are induced tracks, which I could talk a lot about, but I don't think it's important for this one. Well, yeah, I mean, this is worth showing you just because it's so beautiful. So these are the tracks here, and you can see how they're going in and out of focus, and this is just as they're sort of plunging into the crystal. And so these tracks are 3D features that you can see, and you can focus down to different depths and see tracks come in and out of focus. And so if we have different systems that tell us about when rocks are at different temperatures, we can combine that with numerical models that show how temperature changes within the Earth. And then we can convert these cooling rates into erosion rates. And so this is a numerical model showing these isotherms, so lines of constant temperature, below topography. And these black lines are showing some of the commonly used closure depths or closure temperatures of these different systems. And you can even see how the topography is actually influencing the shape of these isotherms. So we can use this method to not only measure denudation, but also measure how landscapes are changing. This is how it works in practice. So we're going to the field. This is from my PhD work. Towards the end of the talk, I'll show you some photos that I collected of me collecting rocks in the Weald, and it's not quite so glamorous. This is rock collecting. It's not very sophisticated. We just use a hammer. It's really just about collecting that block of rock. Then we take it back to the lab, isolate the crystals of apatite. To do this, we take the rock and we crush it to produce sand. And then we use density separation to only select the minerals that float or sink in different liquids with different density. Then we wrap the crystals in these little platinum envelopes. These envelopes are about 300 microns large, maybe 500. And then we heat them up with a laser. And as we're heating up these crystals, the helium that's trapped within the lattice can escape. And we can measure that helium on a mass spectrometer. And so this is a mass spectrometer here, and we're able to measure the very small amount of helium that comes out of these very tiny crystals with a mass spectrometer. Then we measure the uranium and thorium concentrations. This is me posing for a photo. There's actually not a nib on this. And then we can measure the uranium and thorium on a different mass spectrometer to basically get an age. And these different data sets allow us to do very exciting things. This is a nice example from this part of the world. So this is north of Scotland, this area here. And over, well, I think this is actually, this was published here, but the amount of time that went into producing this data set would have been much larger. But each one of these circles shows a borehole that was drilled by the oil companies. And within that borehole, different rocks from different elevations have been collected, or different depths have been collected. And people have run fission track analyses on these different crystals. And so this data set is absolutely enormous. And it's constraining basically thermal histories. Now, I've been working to really maximize the amount of information that we can extract from these types of data sets. And this is an example from this area. And so on the left, I'm showing temperatures back through time. In the middle panel, I'm showing errors associated with these temperature estimates. And then in the right panel, I'm showing the temperature offset. So effectively, the geothermal gradient. It's all happening a little bit quickly. I could try. So yeah, at different times in the past, you can see that the rocks were at different temperatures, effectively. And so we're even able to produce maps that show places that are eroding here, northern Scotland, and these areas stay at high temperatures because the samples are coming from depth towards the surface, whereas in the surrounding sedimentary basins, the rocks are actually being buried by sandstones or by sand that's being shed off the surrounding continents and burying these samples and heating them up. And so we're able to really constrain this source-to-sink system. But when we start to look at the overall pattern of fission track ages across the UK, we can see this big hole here. So this is a problem for the things that I want to do. Right? Ideally, I'd like to have lots and lots of samples from here that have been collected over 20 years, but that's not the case. So yeah, we've been trying to collect data here. This is the extent of the data that we've collected. Yeah, you don't need to read any of it. I'm just showing you that there's only 1, 2, 3, 4, 5, 6 samples from across the whole Weald. And this is something that I'm working on now to try and sort of, collect 100 times more ages across the Weald. And then we can really piece together this erosion rate history. The other component of this work is to try to simulate how the landscape might evolve. And this is a geological map from Gideon Mantle, who was probably one of the most famous Wealden geologists. And he produced this lovely geological map of the Weald, and it was really one of the first maps. Then we can put this into some sort of geographic reference frame and try to digitize these different contacts and produce a very simplified model of how the geology looks today, and project these contacts across the fold of the Weald to predict how these contacts change in space. And then we can use that to calculate landscape evolution. And the basis of this is this transient stream power model. So this is change in elevation divided by change in time equals the uplift. So this is the rock uplift rate minus the erosion rate, where this is K is the erodibility. so how easy the rocks are to erode. A is the upstream drainage area, so this is how much water is coming through a specific point in the landscape. And dz dx is the local slope. I wasn't sure whether to put this in, but I know that some of you are sort of physicists and things like that, so I thought this was interesting for some of you. So yeah, if you're not interested, don't worry about it. I made this. Did I put this video? Yeah, I made this video here with my daughter's watering can to get across this idea of differential equations. So here the water is filling up the watering can, and at some point I increase the flow of the water into the watering can, and then the water flows out more quickly, and the height of the water increases until it reaches some sort of new steady state, and everything's balanced. And then I change the flow of water, and then the water level drops back down again until some sort of new steady state is reached, and now the water level in the watering can is not going up or down. And so this is what's happening when we solve these sorts of numerical models. And so this is what the solution to this equation looks like for a single river. So this is a river profile here, plotted as a function of length along the river versus elevation. And this is the rock uplift rate, so this is how quickly rocks are being uplifted. And so initially the rock uplift rate is very low at 0.5 kilometre per million years, which is 0.5 millimetre per year. And the river stays at a steady state, it doesn't change. This is what we saw in that watering can video. But then at some point the rock uplift rate increases to some new background rock uplift rate. And so this is equivalent to me changing the rate at which the water was filling that watering can. And so initially the river is in steady state, and then there's this increase in rock uplift rate, and the river profiles change and they evolve. And we see this increase in the elevations at high elevations over time, but lower down the river basically stays at a constant elevation through time, just like in the watering can video. And so this is a very simple model that simulates how landscapes evolve, and we can use this simple model and the simple reconstruction of the geology of the Weald to try to simulate how the Weald might evolve through time. And this is the first attempt that the first time I tried to do this. And so this scenario is basically looking at a block that's uplifting, and here the chalk is exposed, and then we start to see the exposure of the relatively soft, the weak Wealden clays, and this escarpment develops. So the escarpment develops like this, and then it migrates outwards from the crest of the anticline, and the whole area becomes very flat because the rocks are very soft, and so they're not able to support steep slopes. And then in the middle of the model, the harder sandstones of the Weald are exposed. I'll play that again. So this is so somewhere here, maybe now, yeah, so this is when we see the Wealden clay exposed, and then this is the chalk retreating, and then this is the sandstones that are exposed in the core of the Weald. So obviously this needs a lot of work, but it's quite interesting that we're able to do this sort of thing. And if we can use the thermo-chronology to constrain these models, it'll be very exciting. What's the time? Have I got a bit more time? Okay. Is everyone okay if I keep going? It's not like students. The students have to be yeah, so this is the figure that I showed before, showing long-term trends in denudation rate or erosion rate across the Weald. And these rates are very, very low. But in the central Weald, and here as well actually, the topography is very, very steep. and this suggests that the erosion rates might be much faster. And yeah, if we think about this model, there might be places that are eroding much more quickly than other places, even though there's no change in the tectonics, right? Just because different lithologies are being exposed at different times. And of course, in the core of the Weald, the sandstones that make up things like the Hastings beds, the Tunbridge Wells sands, the Cookfield stones, these are all interbedded with thinner units of basically clays. And so the geology is very complicated. Around here, there's very complicated geology with these green sand, more erosive units that make up Leith Hill and... There's Leith Hill and what's the other one? That's a little bit... I think so. But Box Hill's chalk, isn't it? Yeah. So it's not chalk, it's the one that's slightly... yeah, so in Balcombe, we see a lot of these small landslides or landslips. And these normally only occur in places that are eroding relatively quickly. And they might be eroding quickly because the rocks are very soft or because the slopes are very steep. And when we look at the LiDAR data from Balcombe, we can see very steep topography. So these are very deep, I wouldn't say canyons, but they're very deep valleys that you really struggle to walk along. There's a lot of small landslides, a lot of trees are falling down into the river, and there are very large clasts that are being transported by storms along the base of the river. These are very active environments, I think, that are eroding much faster than 0.02 millimeters per year. And I think this is partly because we have complex stratigraphy that's revealing different rocks with different strengths over time. So one of the things that I'm very excited about at the moment are these cambering features. So this is a unit in Derbyshire that shows this complex folding, and this folding is forming at the bottom of a river valley. And for a long time, the development of these folds has been debated, and people argue whether these form, whether they're formed during deglaciation, and whether this change in temperature that is expected at deglaciation drives a change in the rheology or how easy it is for these rocks to flow, and that produces these folds and this buckling at the bottom of the valley. Or can topographic stresses drive this deformation? So in other words, can the development of these very deep valleys that we see in places like Balcombe, can that drive stresses to force the rocks to flow and produce this sort of feature? So this is also in Derbyshire that was glaciated during the LGM, whereas down here that there weren't these large glaciers in the same way. This is a sketch showing what people think is happening. So here the clays are flowing towards the valley bottom, and the overriding limestone here is basically riding on top of that clay layer towards the valley bottom. This is an example of a sketch from Freshfields Quarry. And you can see this, so this is by Percival Allen. And you can see this lovely fold that's been identified in the clay. And this has been attributed to valley cambering. So this process of clay flowing into the valley bottom. This is another example in the Wealden clay from the Southwater brick pit. And you can see this lovely fold, and the downslope direction is shown here. And so these folds are developing as the material flows downslope, essentially. This is another sketch showing what we might expect to see. And then this is now a geological map of Balcombe. So I'm going a little bit quickly. So this is Balcombe train station, and the sort of, I don't know, orangey colour is the sandstone, and then at the bottom, this darker colour here is the clay. And here, the sandstone is here, and then right in the middle of this figure, or this geological map, you can see this small island of clay. And so over time, as the landscape continues to erode, this area would get bigger as more and more of the underlying stratigraphy is revealed. And so we went here to try to see if there was any signs of valley cambering and this folding process. And really we wanted to see if there was any evidence for it happening today. This is an example of a river in Balcombe, and maybe you can make out the folds here. There's a fold here and then another one here. It's quite hard to see, and this is why I don't start my talks with pictures of this. This is another really nice example of very steeply dipping clays. This is the Wadhurst clay, so this is the clay below the Ardingly sandstone. And the Ardingly sandstone is perfectly flat. I mean, I'm sure you've seen pictures of it. But the clays can be incredibly steeply dipping. This is an example here, and you can see this folding structure here. This is quite nice. And so this is showing that these clay layers are deforming. And I don't think that these are local features associated with slumping. I think it's a much larger scale phenomenon. And so we walked all the way along this river, and these pink circles are showing the strikes and dips of the clay as we walked along the river. And I'm reasonably convinced that they look like they're orientated parallel to the direction of the bed of the river. Certainly here it looks like the river's flowing more like this, and these look like they're like this. Here maybe like this. I don't know. Maybe it's not so clear. But yeah, this is Balcombe train station here, and this whole area has recently been stabilised because the banks were collapsing. And this is the Balcombe oil well here. So this is in an area that's potentially experiencing modern deformation due to this process. So then I put together a little numerical model to simulate this process. And what this is simulating is a valley that cuts down over time. And as it cuts down, it exposes the softer clay layers at depth. And then you see the clays deforming. And this is a lot like the sorts of models that people would have done if they work on like salt tectonics. I know that's something that lots of people in the oil industry work on. So you can see this. This is coloured based on horizontal velocities, and this is vertical velocities. And you can see this sort of area here where the rocks are really moving upwards rapidly at a rate that's much faster than the surrounding erosion rates. So maybe this is explaining why we see these apparent spatial variations in denudation. And maybe we actually do see spatial variations in the rates at which rocks are moving upwards, and this is due to small-scale deformation. And it also has implications for what might happen if there was a borehole here. Perhaps this is being sheared at depth, and this process isn't really being explored fully. If this process is ongoing and is not a post-glacial phenomenon, it has wide-reaching implications. And then also to understand depth or stresses at depth is important for understanding earthquakes. And I thought I'd very quickly mention that I have been working on these earthquakes around here. So this is the earthquakes that occurred between 2018 and 2019 around Newdigate. And really these are forming or focused along these large faults. But to understand how likely triggering of these earthquakes is, we need to understand the stress state of these faults. And if these faults developed when there was a huge amount of overburden over the area, the stresses on these faults is going to be very different than if there's continuous fast erosion. And so more recently we've been trying to understand the sequence of earthquakes, and we think we see a good correlation now between oil extraction, so this is oil extraction, and the earthquake. So this red line is the cumulative distribution of earthquakes that occurred around Newdigate, and these coloured bars represent oil extraction from different geological units. And I think that there's quite a convincing argument to be made that when the oil is extracted from the Kimmeridgian units, these soft, weak units, there aren't many earthquakes, but when the oil is being extracted from the stronger blue units, the Portland sandstone units, there seems to be this relationship between seismicity and earthquakes. So yeah, that's going to come out soon, and that's with Phil Meredith as well. Okay, thank you all for staying so late. I'm sorry I overran a little bit.